the important question is that how will you treat these components of the tensor mathematically, and it is actually a very involved problem. So, to understand what is actually the involved problem, let us look into the equation. We started with the Navier Stokes equation. We knew that the Navier Stokes equations are very much valid for turbulent flow, of course if the other assumptions like Newtonian fluid and Stokesian fluid they are satisfied, but it is not so easy to deterministically obtain the variables from the original form of the Navier Stokes equation because of the uncertainties in maybe boundary conditions or say initial conditions like that. So, what we concluded is that their statistically average forms are so called deterministic, and therefore we statistically average them. One good thing of the statistically non-average form was that the system of equations were closed. So, number of equations and number of unknowns were matching with each other. Now, we have new sets of equations where the variables are very much deterministic, the statistically average ones, but the equations are not closed because you have now come up with many new unknowns through this term. So, you have 6 extra unknowns, and there is no magical way by which you can have 6 extra equations but for these 6 unknowns. Of course, you may try to write 6 extra equations, but that might give rise to another new set of unknowns. So, closing the number of equations with number of unknowns is one of the very toughest things in statistical averaging. To get a fair idea of this problem, let us consider a very simple type of equation which is not this one, but just for mathematical analogy. Say you have an equation du dt equal to u square. Okay. Of course, this equation has a very simple solution. If you give the initial condition at time equal to t0, what is u, and you can very easily integrate it, one of the simplest differential equations. But let us say you do not want to solve it in this way, you want to solve it with statistical averaging. So, then what you do? You average the left hand side, you average the right hand side. So, what you get out of this? You get the statistically averaged form of the equation as d dt of u averaged is equal to u average square. The problem is that with this averaging you have given rise to a new variable u square average. Of course, you may think that well I will solve it by introducing a new equation, and that new equation you may introduce say by multiplying both the sides with u square. So, then what you get, say you have du dt equal to u square. So, if you multiply both the sides with u, you will get d dt half of d dt of u square is equal to u cube, just multiplying both sides by u, non-average form. Then if you average it, yes, you get a governing equation on averaged u square, but you get a new variable averaged u cube. So, every stage you try to do statistical averaging, you are finding it tremendously difficult to close the system of equations, and that is what is precisely happening here. So, you have after Reynolds averaging in the equation certain terms for which you do not have automatically explicit governing equations, and therefore number of equations and number of unknowns or number of independent equations and number of unknowns are not matching, and the system of equations is not closed. So, that is known as the closure problem in turbulence. This is one of the biggest nightmares that one has to deal with. So, the closure problem in turbulence is that basically you have certain additional terms in the governing equation after Reynolds averaging, and these additional terms do not have explicit governing differential equations. So, you have a mismatch between the number of independent equations and number of unknowns. So, only way in which you may patch up this gap is to make a mathematical or a physical model by which you postulate this term as an equivalent of some other term which you may know or which you may pretend to know by some sort of modeling, and that modeling will not be something which is exactly the physical reality, but it might be an approximation of the physical reality, and that is the job of the modelers in turbulent flow analysis, and that is the job of turbulence modeling. We will not go into the details of turbulence modeling, that is not within the scope of this discussion, but what we will try to do is we will try to see that what is the approximate way in which this term may be modeled. To do that, we will have a deeper look into this Reynolds stress tensor and try to draw an analogy of this with our usual stress tensor. So, if you recall that in our usual stress tensor we had the diagonal terms and off diagonal terms, and the diagonal terms were representative of the so called the normal components and the off diagonal the shear components of the stress. And when we derive the constitutive relationships, we decompose the stress tensor into two parts. One is the hydrostatic component, which was obtained by sort of averaging the diagonal terms, and that was manifested in the form of a pressure which is acting equally from all directions, and a deviatoric component or the deviation from the hydrostatic component. And deviation from the hydrostatic component is something which is important for modeling the constitutive behavior, because that is something which gives rise to the relationship between the stress and the deformation. So, because that is what is responsible for the constitutive behavior in terms of the stress deformation relationship. So, similarly here also you may decompose the stress tensor into two parts. One part is obtained from the diagonals of the terms of the diagonals of the stress tensor, the diagonal of the stress tensor, and that is like the equivalent to the hydrostatic stress tensor component. Here we do not call it hydrostatic because it does not have the same meaning, we call it isotropic component of the stress tensor, and whatever is remaining contribution from the stress tensor we call it the anisotropic component of the stress tensor. So, if we give this stress tensor a name say tau, say Reynolds, so it has two parts, isotropic and anisotropic. It is just equivalent to the hydrostatic and deviatoric, and the anisotropic part should be responsible for the description of the equivalent constitutive behavior in terms of the average quantities. So, when you write the isotropic part is basically minus rho ui prime square plus, so u1 prime square plus u2 prime square plus u3 prime square averaged by 3, that is the mean of the terms in the diagonal, and the remaining is the anisotropic. So, the Reynolds stress tensor is minus rho ui prime uj prime average, it has an isotropic part and an anisotropic part. The isotropic part, let us see how we write the isotropic part. We may write the isotropic part through a definition known as the turbulent kinetic energy. So, turbulent kinetic energy sort of represents the kinetic energy because of the fluctuation velocities in the flow. So, that is defined as just half of u1 prime square plus u2 prime square plus u3 prime square. Therefore, this term which is there in the bracket, it may be written in terms of what? It may be written as, you can write this one as minus 2 rho k by 3. What about the anisotropic part? Now, this anisotropic part we may write or we may describe in terms of what we may describe in terms of an equivalent constitutive behavior, and just by analogy of the form, let us say we want to write it as some equivalent viscosity, which is not actually a molecular viscosity, but some equivalent characteristic times the average rate of deformation. Once that is done, you may substitute this extra term as this is one part which is the isotropic part. So, that is why this delta ij is there, this is only there if j is equal to I, and plus so if we combine these terms, we can write the right hand side, and the right hand side becomes cosmetically this is a greatly relieving form of the governing equation, because it assumes a form virtually the same as the non-average form of the Navier Stokes equation. What are the important changes? One important change is, instead of the pressure you have the average pressure plus a term dependent on the turbulent kinetic energy, and let us say we call it P average equivalent. So, if we are solving it in the same form as that of the Navier Stokes equation, no problem, but whatever P we get, we have to understand that it is not P average, but an equivalent with some term because of the kinetic energy. The other important observation is that the mu in the original Navier Stokes equation is replaced by some equivalent mu, which is mu plus mu t, or you may call it mu effective, and this mu t, which is known as the turbulent viscosity, is contributing to this mu effective. And just this form was originally introduced by Buzenisk, and of course this is just like a hypothesis, it is not that this is exact, and we have discussed that what is the philosophy. The philosophy is a desperate act of closing the system of equations, and then of course it might be written in this form because it is an acceptable constitutive form. We have seen that it satisfies the basic requirements of continuum mechanics, at least in form, but the big question is now the mu t is something which is not known. So, apparently it looks as closed, but it is not a closed system of equations, because you have a mu t which is not a fluid property, which depends on certain conditions in the flow in terms of the statistical averaging of the fluctuations, and therefore there might be an additional description, or there must be an additional description or modeling of this mu t, which is one of the important jobs for turbulent flow modeling. So, the big understanding is that while we were trying to close the system of equations, we came up with certain extra terms, and we are seeing one of the approaches by which this extra term may be cast in the form of the original stress tensor form of the Navier Stokes equation, but it gives rise to some extra term in the equivalent viscosity definition, and that extra term comes out of turbulent fluctuations and their averaging, and therefore it is not so straightforward to have a description of it without having more involved considerations. Now, keeping this in background, we will now see that what are the consequences of these fluctuation velocities, and the big question that we did not answer till now is that why this quantity will be non-zero, because if this quantity is 0, one of the big problems is resolved, and so we have to understand that what is happening which is not making it 0, and clearly we have to distinguish between the terms which are like the isotropic components and the anisotropic components. In this context, we will just remember that sometimes this fluctuation kinetic energy is expressed as a non-dimensional parameter in terms of the kinetic energy of the mean flow at the inlet of a pipe, for example. So if you have at the inlet of a pipe some flow with a velocity say u infinity, then you may have like u1 prime square plus u2 prime square plus u3 prime square divided by u infinity square as a non-dimensional description of the or non-dimensional measure of the inlet turbulent kinetic energy, or maybe at anywhere, and this is known as turbulence intensity. And many times it is considered to be as a fitting parameter for different mathematical models, maybe 5%, 10%, that is what is commonly taken. Now the other important point is the physical description of this ui prime uj prime, and to do that we have to keep in mind that we are now having to deal with situations which have some isotropic component and which have some anisotropic component, depending on whether I equal to j and whether I not equal to j. So let us try to revisit the important definitions of isotropic turbulence and a related quantity, homogeneous turbulence. So when we discussed about homogeneous turbulence, this terminology at least we introduced in the previous lecture, and what we remarked is that if you have a homogeneous turbulence, it means that the turbulence statistics are independent of position. So that means if you have say u1 prime square at a point, then if you go at different points you will get the same turbulence statistics. That means turbulence statistics are invariant under translation. When we say invariant under translation, question is the translation of what? Of obviously translation of the coordinate system by which the turbulence statistics are described. So when it is invariant under translation, that means no matter you translate the coordinate axis to a different location and find out the same quantity in a statistically average sense, they are the same. It does not mean that u1 prime square is same, it means the statistical average of u1 prime square is the same at all locations. Now when you go to isotropic turbulence, isotropic means, as we discussed earlier, direction independence. That means the turbulence statistics are direction independent. And when we say they are direction independent, it means what? Direction independent means that if you have a set of coordinate axes say x1, x2, x3, and you have say u1 prime square, u2 prime square, u3 prime square, like that, some statistically average quantities, there could be many such quantities. Now when you have a rotated coordinate system with x1, new x1 like this, new x2 like this, and maybe new x3 like this, of course orthogonality of the axis that is preserved. Then if you have the u1 prime square with respect to new x1, u2 prime square with respect to new x2, and maybe u3 prime square with respect to this new x3, they are the same. So the statistical description is rotation invariant. Again, it does not mean that u2 prime square is the same, it just means u2 prime square when statistically average remains the same, just like that. So not only rotation, also reflection. So turbulence statistics are direction independent means invariant to rotation and reflection of coordinate axis. Now another important catchword is that for when we are describing isotropic turbulence, in this special case we are also having a constraint that it must also be invariant under translation. So that is an additional constraint over and above this requirement. So this plus it has to be invariant to translation, and from this we may answer the question that we asked in the previous lecture. We asked to ourselves that does it mean that homogeneous turbulence has to be isotropic, number one, or does it mean isotropic turbulence has to be homogeneous? we can clearly see that isotropic turbulence must be homogeneous, because it also has to be translationally invariant, the statistics. On the other hand, there is no necessity, there is no guarantee that homogeneous turbulence will be isotropic. So that is one important thing we need to remember. So with this understanding of isotropy and anisotropy, now what we will do, we will consider that how these ui prime uj prime terms are coming. So let us say we want to describe this with an analogy of the origin of shear stress that we discussed when we were talking about viscosity in one of our earlier lectures. If you recall, we introduced about two important physical origins of viscosity. One is the transfer of molecular momentum between different fluid layers, and the other is intermolecular forces of interaction. Now we are trying to draw an analogy with the transfer of molecular momentum, and here instead of molecular momentum you may just consider the exchange of momentum between eddies present in the turbulent flow. So let us say that you have three different layers with a velocity gradient along a particular direction. Say you have an increasing velocity gradient in the y direction. Let us say that this layer has a velocity along x as u in the average along the x direction. Now there is a fluctuation velocity component which is like v prime of that layer. The average flow may be one dimensional, but the turbulent flow is always 3-dimensional and unsteady. Only the average quantity may be 1-dimensional, 2-dimensional or steady. So because of this fluctuation, what is happening? The fluid element, there is some fluid element which is joining the top layer. What it will do with the top layer? It will try to reduce the velocity of the top layer. Why? Because it is coming from a layer which is having a reduced velocity. So it will try to exchange that momentum with the top layer and reduce the momentum of the top layer in the process. That means because of a positive v prime, you have a negative u prime. That is, the fluctuation in u that is being created because of a v prime from a slower moving layer to the faster moving layer at the top, the act is to have a reduction in u. So if you therefore calculate u prime v prime or v prime u prime, whatever, this product will be negative for this case, positive v prime, negative u prime. Similarly, you may have a v prime along the negative y direction, that is, and fluid element try to exchange momentum with the bottom fluid layer. So when it tries to do that, what it will do? With a negative v prime, you will have associated positive u prime. So again v prime u prime is negative. So in both cases v prime u prime is negative when it is moving to the top and when it is moving to the bottom. Therefore we can say that when you statistically average this u prime v prime, all the negatives add together and it is not, the sum is, the statistical average is not 0 in general. So that is why, see, when we wrote this minus of ui prime uj prime when I not equal to j, and we, when I not equal to j means the deviatoric component, we wrote it in the form of a mu t into this velocity gradient. Here velocity gradient along y is positive and therefore mu t has to be positive, because I prime uj prime when averaged when I not equal to j is itself negative, that negative with the minus becomes plus. Here del u del y in an average sense is positive and therefore mu t has to be positive. However, the situation may change dramatically if you have this type of a situation. Let us say that you have a situation where you are having the central fluid layer like this, the upper fluid layer like this, the lower fluid layer like this, perfectly symmetrical. This is like as if y equal to 0. Now in this case, if you have a positive v prime, it will associate it with a negative u prime. So u prime v prime is negative for this interaction. Let us consider a similar interaction when it comes to a negative v prime and it interacts with the lower layer. So here a negative v prime is associated with what? A negative v prime is associated with a negative u prime, because it comes from a slower moving layer, so it tries to slow it down. So negative v prime and you have a negative u prime. So, u prime v prime product is positive, and if it has a sort of a symmetry in the distribution, then these two effects may nullify each other for such pairs, so that the sum total is 0, and that when it becomes a case, that is ui prime uj prime average becomes 0 if I is not equal to j, then that is what is isotropic turbulence, because then in the turbulence stress tensor of the Reynolds stress tensor you only have the diagonal terms, all the off diagonal terms are 0, and the diagonal terms are because of the anisotropy, because of the isotropy, and the off diagonal terms are because of the anisotropy. So, we can clearly see that what are the possibilities? The possibilities are that this, when this ui prime uj prime they are averaged, either they may be 0 when it is isotropic for I not equal to j, or the average may be negative. And if you just try to draw this in terms of a scatter diagram and try to represent it, say we are plotting v prime versus u prime in two cases. One is isotropic, another is anisotropic. So, when you have isotropic, you see, let us consider one case where you have say a deviation from with a consideration say u prime equal to 0. So, if you have a case with v prime as some positive quantity, you also have a equally probable case with v prime as negative of the same, because the average of u prime v prime taken over all possible values should be 0. So, if you draw a scatter diagram with such cases of points, so these points are what? These points are scattered data. The scatter diagram in the form will look like a circular description, and the reason is straightforward, that it does not have any bias towards coordinate axis. So, you rotate the coordinate axis, you will have a new u prime, you have a new v prime still orthogonal to each other, it is perfectly circularly symmetric. So, this will be the scatter of the data. So, on an average u prime v prime average will be 0. However, when it is anisotropic, the scatter diagram, the scatter of points may be like this. And why it is scattered like this? Because if you calculate the correlation between the two, we have seen that u prime v prime average has a negative correlation, and that is why if you fit a regression line, it will have a negative slope, and that is why this will be the sort of scatter diagram for the anisotropic one. So, by looking into the scatter diagram of u prime v prime or the correlation between u prime v prime was just two examples of ui prime not equal or I not equal to j, ui prime uj prime, and by looking into this type of diagram, it is possible to have a clear picture on the extent of isotropy or extent of anisotropy in the description of the turbulence in the flow. No matter whether it has a whole lot of anisotropy or a whole lot of isotropy, the big question will remain is that how we reflect that within the description of this new unknown that we have introduced in the Navier Stokes equation. And the average, when we said the Navier Stokes equation, we mean the averaged Navier Stokes equation or the Reynolds average Navier Stokes equation. So, the equation that we are talking about now is known as RANS or Reynolds average Navier Stokes equation. So, in the Reynolds average Navier Stokes equation, now we have a situation where we have an extra term. The extra term is because of what? It is because of the momentum exchange between eddies with different fluctuations. So, it is no more molecular momentum exchange, but turbulent momentum exchange, but has a sort of analogy with the molecular momentum exchange. And as we discussed earlier, the molecular momentum exchange has also a sort of similarity with the kinetic theory of gases, that is exchange of momentum between gas molecules. And therefore, by drawing analogy with the exchange of momentum amongst the gas molecules and the exchange of momentum between the fluctuation components of eddies, it is possible to have some simplistic description of how to go about to describe this turbulent viscosity, and that may be achieved by a very simple but phenomenal engineering model known as Prandtl's mixing length model, that we will do in the next class. Thank you.